Let's investigate the field axioms in abstract algebra. The term field is used in physics to describe different things, depending on the context. In this video, we're specifically talking about the abstract algebra definition of a field. And I'm going to write down a list of axioms, and those axioms are the fundamental properties of a field. So those are the defining characteristics. So let's get started. I'm going to use capital F to denote the field. And the field can be thought of as a set. It contains a collection of elements. And I'm going to need two operations with this set to define a field. And one of those operations is addition, and the other one is multiplication. So this is just standard notation for addition and multiplication. I'm going to put some parentheses around here, and that is telling me that I have a field defined with two operations. Now I'm going to go through a set of axioms for addition, and then an analogous set of axioms for multiplication. And then finally, I'm going to go through one axiom that links together those two operations. And that axiom is called distributivity. So a lot of these axioms are going to be familiar to you if you've seen the previous video in the quantum mechanics playlist, where I defined groups, commutative groups, fields, and vector spaces. In that video, I defined fields in terms of commutative groups. But over here, I'm going to explicitly write out all of the axioms. So let's get started. First, let's write down the axioms for this addition operation. I'm going to use the for all symbol. The for all symbol is an upside down A. So for all A and B in the field, I'm going to use A and B to denote some arbitrary elements that are inside this field. For all A and B that are elements of the field, capital F, I want A plus B to also be an element of the field. So this is called closure. This means that the field is closed under addition. If I use the operation of addition to combine two elements together, that resulting element is also an element of the field. So this property is also an essential property of groups. We want this operation, or any operation that we're using to combine elements of the set, to keep the elements inside the set. Otherwise, it's not a very meaningful mathematical structure if you combine two elements and they leave the set. That can sometimes happen. But in this case, in this definition, we are imposing this as a fundamental property. The next fundamental property I'm going to write down is associativity. So I'm also going to start off with the for all symbol. For all A, B, and C that are elements of the field, I want A plus B evaluated first and then added to C to be equal to A plus the sum of B and C. So the only difference between these two lines over here is that over here I am first evaluating the sum of A and B and then adding that to C. And over here I am first evaluating the sum of B and C and then adding that to A. So this is known as the associative property or associativity. And addition is associative for a field. Next, I want to introduce a property that is linked to the identity. So what I want is there to exist an identity element. And specifically, I'm talking about the additive identity. There's not just one type of identity in a field. So first, we're going to talk about the additive identity. So I want there to exist, I'm going to use a backwards facing E. This means there exists an element, which I'm going to denote by 0, and that is the additive identity. It is an element of the field such that, so this colon can be read as such that, there exists 0 in the field such that for all elements in the field, and A is just some generic element of the field, I want A plus 0 to give me back A. So adding the additive identity does not change the element. And that's true for all elements in the field. So this notation over here, 0, is just a carryover notation from basic arithmetic. 0 is the additive identity in basic arithmetic. So now that we have the existence of an identity, we can also define inverses. We want every element to have an inverse. And specifically, we want it to have an additive inverse. So for all A in the field, I want there to exist a additive inverse, which I'm going to denote by minus a, which is the same as negative a, and that also has to be inside the field. So there exists a additive inverse in the field such that if I take a and I add it to its additive inverse, that's going to give me back the additive identity. So this is the inverse and this is the identity. And this actually takes care of subtraction. So alternatively, we could define a field with addition and subtraction, and analogously multiplication and division. But that is actually taken care of by this inverse property over here. So for all a in the field, there exists a negative a, or a minus a in the field, such that a plus this negative version of a gives back 0. Now, I also want to impose one more condition, and that condition is called commutativity. So for all a and b that are elements of the field, I want a plus b to be equal to b plus a. So the order does not matter for addition. That is the property of commutativity, or the commutative property. And if this condition is satisfied, then in group theory, we call that an abelian group. So an abelian group is the same as a commutative group. If this condition is violated, then we have a non-commutative group or a non-abelian group. So that is the standard vocabulary that we use to describe this. So these axioms over here, these 4 conditions over here, these are enough to call this a group, specifically an additive group. This is a group under addition. And with this additional axiom over here, we have a commutative group or an abelian group. So that is what we have over here. A field has to have an additive group. It has to have an abelian group under addition. But it also has to have some analogous properties for multiplication. And now let's write down those analogous properties. So for this property, for closure, we also have an analogous property in multiplication. For all a and b that are elements of the field, we want a times b, or the product of a and b, to also be an element of the field. So this is analogous to this guy. The only difference between these two properties, or these two axioms, is that here we have an addition sign, and here we have a multiplication sign. So both addition and multiplication are closed. Or you could say the field is closed under addition, and the field is closed under multiplication. Now let's write down the analogous associative property. For all a, b, and c that are elements of the field, we want a times b times c. So first we're grouping a times b together. We want that to be equal to a times b times c. So over here we're taking the product of b and c, and then we're taking the result of that and the product with a. And on this side we're taking the product of a and b. We're first evaluating the result of that, and then we're taking the product with c. So this grouping does not matter. That is analogous to this over here. All we've done is we've changed the plus sign to a multiplication sign. So addition has changed to multiplication. So associativity is satisfied for both of these operations. Now we're going to have to make some changes when we look at these properties over here. So the additive identity is not the same as the multiplicative identity, but we need there to exist a multiplicative identity. So I'm going to write down there exists a multiplicative identity, and I'm going to denote that identity by 1. So there exists 1 in the field, such that for all elements in the field, what do I want? I want any element A in the field multiplied by 1 to be equal to that element. So multiplication by 1 doesn't change the element. This is analogous to addition by 0. So addition by 0 and multiplication by 1 have the same effect. They don't change the element. So that is the property of the identity element. And in general, the two identities, the additive identity and the multiplicative identity, they're not equal to each other. They're distinct elements in the field. For normal numbers that we're used to in arithmetic, right, the more intuitive numbers that we're familiar with from our childhood, those numbers have this property. 0 and 1 are not equal to each other. They are distinct elements. Now let's have a look at inverses. We're going to have to make a modification over here. For inverses, we're going to have to exclude 0. So I'm going to write down for all a not equal to 0. So everywhere else where I've had the for all symbol, I've just written for all elements in the field. But now what I'm doing is I'm specifically stating for all elements that are not equal to 0. That's every other element excluding 0. So for all elements that are not equal to 0, all non-zero elements, I want there to exist a inverse. And how am I going to denote this inverse? I'm going to write it like this. A with a -1 in the superscript. It's like raising a to the power of -1. And that notation comes from the reciprocal. The reciprocal can be thought of as the multiplicative inverse. So this has to also be an element of the field. So for all non-zero elements, I want there to exist a multiplicative inverse such that if I multiply a by its multiplicative inverse, or by its reciprocal, I get back the multiplicative identity. And this is the identity over here. This is the multiplicative identity 1. And this is analogous to what we have over here. Adding the additive inverse gives back the additive identity, and multiplying by the multiplicative inverse gives back the multiplicative identity. That's a bit of a mouthful, so it's easier to say subtracting off the same number gives you back 0, and multiplying by the reciprocal gives you back 1. So that's what we're familiar with from our intuition about how numbers work. Now, we also want commutativity. So I'm going to write down commutativity over here. And so what we have is for all a and b in the field, we want a times b to equal b times a. So now we have, in these blue axioms over here, we have a group, and it's a commutative group. It's an abelian group, in other words. But it's not all the elements. It's all the non-zero elements. So what can we conclude from these sets of axioms? These sets of axioms tell us that a field consists of an additive group, and that additive group is commutative. So we need the field to be, to form, all the elements in the field have to form a commutative group under addition. And all the non-zero elements of the field have to form a commutative group under multiplication. So in disguise, a field is actually the combination of two groups. But we also need one final axiom to link these guys together. And that final axiom is distributivity. So I'm going to write that axiom over here. For all A, B, and C that are elements of the field, I want A times the sum of B plus C to equal two terms. I want to distribute this A to B and distribute this A to C. So I'm going to have A times B by itself plus A times C by itself. So all I've done here is distributed this A. Multiplication is distributed over this addition. So what is this side telling me? It's telling me that if I take the sum and then multiply by A, that's the same as multiplying by A individually and then taking the sum. That is the property of distributivity. And sometimes you might see distributivity from the left and distributivity from the right. So sometimes it is actually different. Sometimes these are not the same statement. But because we have commutativity for addition and commutativity for multiplication, it doesn't matter. The order does not matter. And alternatively, sometimes in these definitions, you can see this swapped around. You can have the 1 specifically put here. So we have 1 times A. Or over here, we would have 0 plus A. You can swap these guys around, and that's actually the same. That is the property of commutativity. You can see how commutativity shows up implicitly all over the place, because it's a very useful property to have. And it's one of those axioms that we demand from both addition and multiplication when we're defining a field. So all of this here, these are the axioms of a field. Now what I want to do is I want to show you some examples of some fields that you're actually familiar with already. So first let's write down something that is not quite a field. So something that is almost a field. Let's have a look at the natural numbers. So this is the notation for a natural number. The natural numbers in this definition are all the numbers starting from 1. So 1, 2, 3, 4, and so on. These are the counting numbers, the numbers that you can have on your fingers. So these, in most civilizations, were discovered first. So what we have over here are the natural numbers. In some definitions, 0 is included over here. But I'm going to use the definition where we begin from 1. So this begins at 1, then 2, then 3, and so on. Let's have a look at these axioms and see what is satisfied over here. Well, we have closure. Adding 2 of these natural numbers together is going to give you another natural number. Associativity is also fine. But have a look at this axiom over here. We're in trouble because 0 is not included in this definition. So if I expand the definition and I include 0, then I have an additive identity. But what about over here? I'm in trouble again because I don't have an additive inverse for all the elements. So I have to expand this definition. I have to include more elements in the set. I need to have negative numbers. And if I include 0 and the negative numbers, that's going to give me the integers. So the integers will satisfy this axiom over here. So the integers are closed under addition. They satisfy the associative property for addition. There is an identity element. 0 is an integer. And if you add 0 to any integer, you get back the same integer. What about this property? If you just take the minus or the negative version of all the integers, then you have your inverse. And if you take, for example, an integer like 3, and you subtract off 3, that's the same as adding minus 3 or adding negative 3. And that's going to give you 0. So this property holds for the integers under addition. And the addition of integers is also commutative. So we have all of these guys here. So what we can actually do is we can write something very special. I'll use this notation from the previous video. The integers, which are denoted by this fancy z, under addition actually form a abelian group or a commutative group. But that's not sufficient. That's not enough. We need another group. We need a group for multiplication. We need a multiplicative group that excludes the 0 element. So let's have a look over here. Let's see if the integers satisfy these properties over here. Closure is satisfied. If you multiply 2 integers, you're going to get another integer. Associativity works for multiplication. What about this over here? We have a multiplicative identity. 1 is an integer. So if we multiply by 1, we're not going to change the integer. But what about this property? For all the non-zero integers, is there a multiplicative inverse? There is not. This is not satisfied by the integers. You have to expand to all of the rational numbers. The rational numbers are going to allow you to satisfy this property. So let me write down something first. The field F needs to be a commutative group under addition. And we also need one more property. We need the field excluding the 0 element under multiplication. That also needs to be an abelian group. So I'll group all these guys together. All these guys are abelian groups. So they are very special because they are abelian groups. They satisfy all of the group axioms, all of these guys here for addition, and they also satisfy this one over here. Except for this guy, we have multiplication, and we're excluding the 0 element. But over here, we run into trouble. When we're looking at the integers under addition, we run into trouble with this axiom. So that would violate this property. We would not have a multiplicative group inside this field. So that means we have to expand our set. We have to include more elements. And if we do that, then we get the rational numbers. And that's denoted by this fancy Q. So the rational numbers are a set of all numbers that can be written as the ratio of 2 integers such that the bottom integer, the integer that we're dividing by, is not equal to 0. Because you can't divide by 0. That is actually why we have to exclude 0 over here. 0 does not have a multiplicative inverse. Or in other words, you can't take the reciprocal of 0. 1 divided by 0 doesn't make sense, or 1 over 0. There's no agreed upon definition for that kind of operation. So the rational numbers, they do satisfy this axiom. All you have to do is take a reciprocal. For any rational number, all you have to do is swap the numerator and the denominator. That reciprocal is the multiplicative inverse. And if you take a rational number and multiply it by its reciprocal, you will get 1. So this is satisfied for the rational numbers. And multiplying rational numbers is also commutative, and distributivity is also satisfied for the rational numbers. So the rational numbers are the first example that we've encountered that satisfy all of these axioms. They are a field. And they're actually an infinite field, because there's an infinite number of elements inside this field. But there's some problems with the rational numbers. If you were to plot out the number line, where all the numbers live, there are going to be some holes. And those holes are actually irrational numbers. So if you take the limits of sequences, you will get irrational numbers. I'll give you some examples. The square root of 2, that is an irrational number. You cannot write that as the ratio of two integers. So that is a problem immediately. Also, some common numbers that we're used to dealing with, pi, the constant for a circle, Euler's constant, or Euler's number, e, and also, if you're dealing with Fibonacci sequences, the golden ratio, phi. All of those are irrational numbers. So those are holes in the number line that we need to fill up. And if we fill up all those holes, then that's going to give us the real numbers. So over here we have the real numbers, denoted by a fancy R. But the real numbers, even though they filled up all the holes, that is the entire number line, the entire real number line, we still have some problems. If you want to solve equations, there are even simple polynomials cannot be solved with just the real numbers. You're going to run into problems, especially when you have to take the square root of a negative number. If you have to take the square root of a negative number, you're going to run into problems. You're not going to be able to do that working just within the real numbers. So we have to expand this definition again. We have to include more elements into the set. And we have to include the imaginary unit I. And if we take a real number plus an imaginary unit I times a real number, that's in general going to give us a complex number. So I'll denote that by a fancy C. So over here we have a fancy C. So these are the rationals, the reals, and the complex numbers. And all of these guys are fields. These guys satisfy all of the axioms for a field. These guys over here are groups. So here we have abelian groups. And you can find two abelian groups inside the definition of a field. So if you just consider addition, you can actually consider this guy to be an abelian group under addition. It's the same for the real numbers and the complex numbers. And if you ignore 0 in each of these guys, all three of these guys have a 0 element. So 0 is a rational number, it's a real number, and it's a complex number. If you exclude 0, then you have a multiplicative group. And that multiplicative group also has commutativity. So you have an abelian group under multiplication for all three of these guys. So these are some examples of infinite fields. These guys are actually not the same type of infinity. You have countable and uncountable infinities. So they're not the same size. They don't have the same cardinality. So the important thing to remember is that these satisfy all of these axioms, all of the field axioms. So what I'm going to do is I'm just going to read these axioms in plain English to finish off the video. And then in the next video, we're going to have a look at more examples of groups and other interesting structures in abstract algebra. So let me read through these guys in plain English so we don't have to worry about all this complicated notation. For all A's and B's in the field, A plus B is also an element in the field. For all A, B, and C in the field, A plus B, evaluated first, then added to C, is the same as A plus the sum of B plus C, evaluated first. That's associativity. We have closure and associativity. Then, there exists an additive identity, which we denote by 0, in the field, such that for all elements A in the field, A plus 0 is equal to A. Adding the additive identity doesn't change the element. And there exists a unique additive identity. For all A in the field, there exists an additive inverse, denoted by minus A, or negative A, in the field, such that A plus its additive inverse is equal to the additive identity 0. Over here we have commutativity. For all A and B in the field, A plus B is equal to B plus A. The order of addition does not matter. You get the same result. Over here we have closure for multiplication. For all A and B in the field, A times B is an element of the field. Over here we have associativity for multiplication. For all A, B, and C in the field, A times B, evaluated first, and then multiplied by C, is the same as A times the result of B times C. The associative property holds for multiplication. Then over here we have the existence of an identity element for multiplication. There exists an element which we are calling the multiplicative identity, and we're denoting that element by 1. There exists 1 in the field such that for all A in the field, A times 1 is equal to A. So multiplying by the multiplicative identity doesn't change the element. Now let's have a look at this axiom. This is the existence of inverses for all non-zero elements. For all A not equal to 0, or for all non-zero elements of the field, there exists a reciprocal or a multiplicative inverse in the field such that A times the multiplicative inverse is equal to the multiplicative identity. And the multiplicative identity is denoted by 1. Now let's have a look at this commutativity property. For all A and B in the field, A times B is equal to B times A. The order does not matter when you're multiplying numbers. And finally, the distributive property, which links together the two operations of addition and multiplication. For all A, B, and C in the field, A times the sum of B plus C is equal to A times B plus A times C. So over here we have A times B and A times C evaluated first, and then we take the sum. And on this side, we take the sum first, and then we multiply by A. You can think of this as distributing the A over to both B and C. That is why this is known as the distributive property or distributivity. So in essence, a field consists of two commutative groups with this distributive property over here. This group, this additive group, includes all of the elements, and this group over here, this multiplicative group, excludes the 0 elements. So all non-zero elements form a group under multiplication, and that group is a special type of group. It is a commutative group. We've also seen how we can form these infinite fields over here. We started with the natural numbers, then we had to look at the integers under addition, and then we had to look at what these axioms can also be summarized as. The field under addition is also an abelian group, and all the non-zero elements in the field under multiplication is also an abelian group. All these guys are abelian groups. This is not a group, and this is not a field. We don't have the necessary criteria satisfied. The axioms are violated. But over here, all of the axioms for a field are satisfied. So the rational numbers, the real numbers, and the complex numbers are all examples of fields, and they are infinite fields. You can also have finite fields. Those are fields with only a finite number of elements. But in general, what we want to know is that the 0 and the 1 element inside that field, they're not necessarily equal to each other. The additive identity and the multiplicative identity can sometimes be different elements. And in general, we want them to be different elements. That gives us a lot of consistent properties. So these are the fundamental axioms of a field. And other properties of a field follow from these axioms. You don't have to explicitly state them because they can be proven using these guys. But these are the essential properties for a field. You can find other videos where we discuss abstract algebra in the quantum mechanics playlist. If you click over